Good day, everyone. My name is John W. Jones. I'm a member of the Hydrologic Remote Sensing Branch of the U.S. Geological Survey's Water Mission Area. It is my pleasure to introduce the surface water and wetland remote sensing component of the Saline Lakes Integrated Water Availability Assessment, which I will refer to as the IWAA. Given stakeholder expressed priorities and discussion among project team members, there are three primary objectives for the project's remote sensing science component. The first is to generate time series observations of lake wetland inundation patterns. The second is to generate time series estimates of lake volume change to aid water quantity assessment. And the third is to extend understanding gained at intensive sites to lakes throughout the ecosystem. As an example, we aim to establish volume change estimates not only where and when adequate topobathymetric and water level data are available, but also for locations and time periods when those data are lacking. We must use systematically collected, well-calibrated, openly available satellite imagery to generate consistent, long-term time series data on inundation extents and storage volume changes. Fine resolution commercial imagery collected on demand can be used to evaluate accuracy of water extents based on coarser resolution inputs. A pair of NASA satellites carrying the Moderate Resolution Imaging Spectroradiometer, referred to as MODIS, have very high spectral resolution, low spatial resolution, and have imaged the entire globe twice daily since 2002. These characteristics of high spectral resolution and temporal frequency, but low spatial resolution, reflect common trade-offs in satellite imaging technology. 8 satellites in the Landsat series have finer spatial resolution and comparable spectral resolution to MODIS for water extent mapping purposes. 1 or 2 Landsats of this quality have been in operation every day since 1982. Revisit frequencies for Landsat vary by as little as a day to as much as 16 days, depending on latitude and time period. The European Space Agency has operated multiple Landsat-like satellite systems since 2016. When used in combination, the Landsat and Sentinel satellites create global coverage with an approximate repeat frequency of 3 days. Maxar Worldview commercial satellites have very high spectral and the highest spatial resolution of any satellites we use. Unlike the other systems, however, they don't systematically image the entire globe. High-quality Maxar commercial imagery may be obtained by civilian federal agencies by request through the Department of Defense under Next-View licensing and are not guaranteed. In 2024, our requests for monthly Maxar collections were honored for 1 of the intensive and 3 intermediate lakes identified by the Saline Lakes IWAA team. This affords episodic spot checking of water extent products operationally produced by USGS and NASA. DSWE and DSWX stand for Dynamic Surface Water Extent, an umbrella term, if you will, for algorithms and data products designed to monitor surface water extent from local to near global scales. Importantly, the focus is not just satellite picture elements, or pixels, that are entirely covered by water and nothing else, but also on subpixel mixtures of water, vegetation, and soil. The DSWE algorithm is efficient, data light, and training data free to afford global processing over long time periods. DSWE produces data with classes selected to represent the confidence with which it interprets the presence of water on the landscape. White areas have no surface water present. Dark blue areas are labeled open water, high confidence. These are areas where 5 independent tests applied to each pixel all indicate the entire pixel is covered by nothing but water. Light blue pixels are open water moderate confidence because a subset of test results are positive. This occurs where the entire pixel is covered by water that may contain a great deal of sediment, has bright soil substrates, or has a rough surface, such as rapids. Green colors represent partial surface water pixels, where there is a mixture of water, vegetation, and/or soil. Darker green areas are partial surface water pixels with larger amounts of water relative to the lighter green partial surface water pixels. The 2 DSWE examples on this slide are from Everglades National Park in Florida in early November and late December 2010. The November case is primarily shaded in greens and blues, while the December case is a majority white. The area was generally wetter in November and drier in December. Targeting partial surface water detection makes DSWE a useful wetland inundation algorithm in addition to an open water one. Verification of partial surface water detection is no trivial matter. I'm using Everglades examples because decades of measurements from hundreds of surface water, groundwater wells are available there to verify that the results generated by DSWE are close to the actual conditions. Mudflats of terminal lakes pose remote sensing challenges as well. Our activities in this IWAA are important for DSWE assessment because we are adding ground-based and other verification data from mudflats in the Great Basin. If you're interested in working with DSWE, freely distributed Landsat-based DSWE data are operationally generated by the USGS for the United States with a period of record from 1984 to present. The MODIS Optical Global Water Intelligence, or MOGWI, is an example of a global lake monitoring system that relies on DSWE as adapted for MODIS. It was developed in collaboration with the National Geospatial Intelligence Agency and is operated by the U.S. Army Corps of Engineers. Because of the coarser spatial resolution of MODIS, only lakes larger than 10 kilometers squared are included in this system. Since optical systems cannot penetrate thick cloud cover, 8-day composites are made from twice-daily MODIS images. This web tool displays the location of lakes larger than 10 kilometers squared and indicates the current size of each lake relative to its average size at the time of year when the dashboard is accessed. This is based on 20-plus years of observations. Solid green circles indicate the locations of lakes that are currently approximately as large as their average size. Upward pointing blue triangles indicate lakes that are above average size, and downward facing red triangles indicate lakes that are below average size. I accessed MOGWI on November 4th, and it indicated that Summer Lake's size was below average for that time of year. The historic data record is available for each lake, allowing a user to observe patterns of lake area variation from the start of the MODIS record. MOGWI compares the lake's MODIS DSWE estimated surface area on an 8-day time step to its 8-day averages across all years. Based on my November 4th query, last year the drying trend for Summer Lake was close to the long-term average. This year, on the other hand, Summer Lake dried more rapidly than average and to the same small size as in July 2021. These data can be downloaded in graphic and tabular form. This system is currently only available to federal employees who request access through a website link provided at the end of this presentation. DSWX is a near global product based on multiple satellite missions and sensor types. One DSWX input is HLS, which stands for Harmonized Landsat and Sentinel-2, a combination of US Landsat and European Sentinel-2 satellites that yield a median revisit type of approximately 3 days. DSWX products are forward processing only, meaning they don't have the 40-plus year period of record associated with the US-only DSWE product. However, an animation of the DSWX HLS output for the first few weeks of production, beginning in April 2023, illustrates the Earth's rotation under the orbit of 3 satellites. DSWX water extent data are more extensive and frequent than is possible with Landsat satellites alone. A radar-based DSWX product went into production in October 2024. This adds even more frequent coverage, including all-weather capability for the open water class. DSWE and DSWX performance is evaluated through comparison with coincident high-resolution imagery and field data. Because DSWX is a NASA-funded project and I am its principal investigator, this IWA project has access to planet data, which has near-daily coverage but lower spatial resolution and spectral sensitivity than Maxar. Regardless, DSWE, DSWX, Maxar, and planet data will all be compared with GPS points collected along water's edge by the Saline Lake IWAA Prey Availability Team during their field campaigns. Preliminary analysis of data they collected for Lake Ebert in 2024 show good agreement with the DSWX open water high confidence class. If you're willing to get your boots wet and help evaluate DSWE, DSWX data by collecting water's edge or depth information, or helping with sensor operation, please reach out to me. It is unfortunate that inaccessibility of water's edge locations, where some of the most dynamic extent changes and mud-flat saturated soils occur, precludes frequent collection of water's edge data in these areas. This reinforces the need to deploy in-situ temperature and inundation sensors that I have already tested elsewhere. Derivatives of DSWE time series data yield useful information for a variety of purposes. One derivative, called proportions, is the frequency of observed inundations over a selected time period expressed as a percentage. We can calculate proportions by individual or combined DSWE water classes. The combined result is referred to as total surface water, which we animated for areas around 11 selected Iowa lakes, including the open water and marshland areas of Harney and Malheur. The 90th and 50th percentiles of Lake Ebert open water high confidence proportions alone clearly portray the variability that has occurred there over the past several decades. These DSWE derivatives are useful for spatially distributed trend analysis, bathymetric mapping, hydrologic modeling, and, as a practical matter for this project, in situ sensor placement design. The production of annual proportions for all of the continental U.S. has been completed, and we are working to publicly release these data. Extent alone does not directly provide volume. However, in combination with adequate topobathymetry and/or satellite-based altimetry of stage, volume change estimates are possible. The Surface Water Ocean Topography, or SWOT mission, is designed and operated to estimate water surface heights. Detailed discussion is beyond the scope of this presentation. However, lake data from this satellite, which launched in December of 2022, started being released a few weeks ago. I added SWOT-based Lake Ebert height estimates to the data record compiled by project member Ramon Naranjo. Procedures to combine these data with DSWE to estimate volume changes will be investigated in 2025. In summary, this past year, an image database for the terminal lakes was assembled from multiple government and commercial satellite sources. Although relatively coarse in spatial resolution, a growing global record of large lake surface area dynamics is available through Mogwai. In addition, 24-year records of finer resolution total surface water inundation frequencies have been generated from Landsat DSWE for select lakes, and a 40-year record on annual total surface water proportions for all of the continental United States will soon be publicly available. Examination of these frequencies and high-resolution imagery, in combination with field data contributed by project members, has afforded insights regarding DSWE use for saline lake tracking, as well as improved guidelines for ground data collection and DSWE/DSWX accuracy assessment going forward. Volume change estimation procedures are an additional research focus for 2025. There is information on the web about the various products I discussed in this presentation. If you are interested in helping collect data on the ground, you can reach me at jwjones@usgs.gov. Thank you for your interest and attention.